Let's now define a transformation group. A being a symmetry transformation, then A composed B is also a symmetry transformation. Therefore, symmetry transformations form a group. A transformation group consists of a set of transformations and a binary composition operation between two elements of this group. It must have closure so that transformations, when composed, they still are in the group. They must be associative, have an identity, and have an inverse. And this is a very important part. So all group transformations must have an inverse. For instance, a rotation group, we have 90-degree rotations. All the group transformations here are satisfied. In the flip group, where we just flip horizontally and vertically, are these all the transformations of the group? The answer is no, because when you combine a horizontal flip and a vertical flip, you get a 180-degree flip, which is not in the group. Then we have to add it, so now we have a group transformation. Now this is a group, because all transformations, when composed, they become transformations that are in the group. There are also commutative or non-commutative groups. The commutative groups are called abelian groups. For instance, is this rotation group an abelian group? And the answer is yes, because the operations commute. Now consider adding flips, vertical, horizontal, diagonal, and rotations. Is this a group? Yes. Is this a commutative group? No, it's not an abelian group. For instance, horizontal flip and 90-degree flip against 90-degree flip and then horizontal flip give you different transformations. Groups can be finite or infinite. For instance, the rotation group of the point clouds in 2D is an example of an infinite group. These are also known as Lie groups. Groups can also have subgroups, so that is a subset that also forms a group. A very important group is a general linear group, where the inputs are n-dimensional vectors, and the transformations are n by n invertible matrices. The binary operation here, composition, is the matrix product. And you can verify that it satisfies all group properties. We also note that for vectors of dimension greater than 1, the transformation is non-abelian. It's not commutative. In the general linear group, all transformations can be defined as square matrices, and all transformations are linear. Any subgroup of the general linear group is a linear group. An example of a subgroup of a general linear group would be then the permutation matrix A. Now let's see another linear group that takes m by m colored images. Remember, the color images are going to be vectorized. So essentially, any transformation over this linear group is going to be a matrix multiplication over this vector. Let's consider a dog example again. We have this colored dog. We rotate 90 degrees, which is a linear transformation over this vector, to another vector. If you unvectorize, you see the dog rotated. An interesting question is if there is a linear transformation in the linear group that is equivalent to a 45-degree rotation in the space of m by m RGB images. And the answer is no, because those transformations are not invertible. A question I get asked is, what if we also scale when we rotate? And the answer is still no, because the scaling has to have compositions and therefore should be applied by itself and under compositions, which will make the dog blow up over the picture, so no 45-degree rotations. So what's a transformation that's invariant to all group transformations? It's essentially the average transformation of the group, and that's called the Reynolds operator. The Reynolds operator is likely not in the group because it often is not an invertible transformation. But the Reynolds operator has an important property. T bar is a Reynolds operator, and if you think about any transformation from the group, then if you right multiply the Reynolds operator by the transformation of the group, we get still the Reynolds operator. So it's invariant under these transformations. Let's see an example. Here we have the rotation group over 2 by 2 images, which are 4-dimensional vectors. Now let's apply the rotation to the original image. So this is the original image. Here's a 90-degree rotated, 180 rotated, 270 rotated. Now let's construct the Reynolds operator, which is the average of all transformations in the group. This is the Reynolds operator. Now let's right apply the transformations over the Reynolds operator, and we can see that the Reynolds operator remains the same. We can prove this invariance by the fact that it's an average over all transformations of the group and all the transformations are invertible.